common sense is useless, worse than useless. It's actively misleading when you're trying to understand the universe, and Richard Feynman knew this better than almost anyone. He spent his entire career fighting against common sense, showing people that reality doesn't work the way their brains insist it should. Here's what Feynman understood. Your common sense was built for throwing rocks and picking berries. It was not built for understanding atoms or light or time. And when you try to use common sense to think about physics, you get everything wrong. Everything. Let me show you what I mean. Imagine you're holding a ball, you throw it. Where does it go? Your common sense says, the ball goes forward because you pushed it. The push made it move. When the push stops, the ball should stop. That makes sense, right? Wrong. Completely wrong. The ball doesn't need a push to keep moving. The ball keeps moving because nothing is stopping it. If you threw that ball in empty space, far from any planet or star, it would keep going forever. Forever. Never slowing down. Never stopping. Same speed. Same direction. Forever. Your common sense says, that's impossible. Things don't just move forever. They slow down. They stop. But that's only because you've never experienced true emptiness. Everything you've ever thrown has been in air. Air pushes back. Air slows things down. Friction exists. So your brain built a model where moving things naturally stop. But that model is wrong. Newton figured this out centuries ago. An object in motion stays in motion unless acted upon by an outside force. That's not common sense. That's completely anti-common sense. And it's true, here's another one. You're sitting still right now, not moving, just sitting there reading this. Common sense says you're at rest. Zero velocity, stationary, but you're not. You're moving at about 1,000 miles per hour because the Earth is spinning. You're also moving at 67,000 miles per hour because the Earth is orbiting the Sun. You're also moving at 500,000 miles per hour because the solar system is orbiting the galaxy. You're also moving at over 1,000,000 miles per hour because the galaxy is moving through space. You are screaming through the cosmos at insane speeds right now, this very second, and you feel nothing. Why? Because motion is relative. There's no such thing as absolute rest. There's no such thing as absolutely still. When you say you're not moving, you mean you're not moving relative to the Earth. But the Earth is moving relative to the Sun. The Sun is moving relative to the galaxy. Everything is moving relative to something else. There is no preferred reference frame. No cosmic speedometer that tells you your true speed. Speed only makes sense when you compare one thing to another. Feynman loved this. He loved pointing out that our intuitions about motion are completely provincial, limited, built for our tiny experience on this one planet. Now watch this. Here's where it gets really strange. Light. Common sense says light is like everything else. If you're moving toward a light source, the light should appear to come at you faster. If you're moving away, it should appear slower. Just like sound. Just like throwing a ball from a moving car. Makes sense, right? Nope. Light doesn't work that way. Light always moves at the same speed. Always. No matter how fast you're going, no matter which direction you're traveling, light always approaches you at exactly 186,282 miles per second. Always. If you're standing still and you measure the speed of light, you get 186,282 miles per second. If you're in a rocket ship moving at half the speed of light and you measure the speed of light, you get 186,282 miles per second. Not faster, not slower, the same. This makes no sense. This violates every intuition you have about how speeds should add up. But it's true. Einstein built his entire theory of relativity on this one weird fact. Light speed is constant. And if light speed is constant, then everything else has to bend to accommodate it. Time has to stretch. Space has to compress. Mass has to increase. Reality itself has to warp and flex just to keep light moving at the same speed in all reference frames. Your common sense says that's insane. And it is insane. But it's also correct. We've measured it, we've tested it, every experiment confirms it. Light speed is invariant. Here's what Feynman said about this. He said, "I think I can safely say that nobody understands quantum mechanics." And he meant it. Not even the people who use quantum mechanics every day truly understand it in the common sense way. Because quantum mechanics doesn't make sense. It can't make sense. It operates on rules that are completely alien to human intuition. Let me give you an example. Take an electron. Common sense says an electron is a tiny ball, a little particle. It has a position. It has a velocity. It's somewhere doing something. Wrong. An electron is not a tiny ball. An electron is not in one place. An electron is a cloud of probability spread out through space. It doesn't have a definite position until you measure it. And when you measure it, the act of measuring changes it. Before you look, the electron is everywhere it could be, all at once. It exists in multiple states simultaneously. It's here and there and over there, all overlapping, all interfering with each other. This is called superposition. And it's not a metaphor. It's not a convenient fiction. It's what actually happens. Electrons genuinely exist in multiple states at once until you observe them. Then they collapse into one state, the one you see. Here's the kicker. You cannot know both the position and the momentum of an electron at the same time. Not because your equipment isn't good enough. Not because you haven't figured out the right technique. Because the universe won't let you. It's impossible. Fundamentally impossible. This is the Heisenberg uncertainty principle. And it's not uncertainty in the sense of not knowing. It's uncertainty in the sense of the electron itself doesn't have both properties simultaneously. The more precisely you know where an electron is, the less precisely you can know how fast it's moving. The more precisely you know its momentum, the less precisely you can know its position. This is built into the fabric of reality. Your common sense says, that's wrong. Everything has a position and a velocity. How can something not have both? But common sense is wrong. Reality doesn't work that way. Feynman had a great way of putting this. He said if you think you understand quantum mechanics, you don't understand quantum mechanics. Because understanding, in the normal sense, means building a mental picture that makes intuitive sense. And you cannot do that with quantum mechanics. You can learn the math. You can make predictions. You can build technologies based on it. But you cannot make it make sense. Let me show you why. The double slit experiment. This is the experiment that breaks everyone's brain. Here's how it works. You take a barrier with two slits in it. You fire electrons at the barrier one at a time. Each electron goes through one slit or the other. You'd expect to see two piles of electrons on the screen behind the barrier. One pile from each slit. But that's not what happens. You get an interference pattern. Stripes. Light and dark bands. The kind of pattern you only get when waves overlap and interfere with each other. But wait. You're firing one electron at a time. Each electron is going through one slit. There's nothing for it to interfere with. So how do you get an interference pattern? Here's the answer. Each electron goes through both slits simultaneously. It interferes with itself. The electron exists in a superposition of going through the left slit and going through the right slit, both at once. And those two possibilities interfere with each other, creating the pattern you see. Now here's where it gets truly bizarre. If you put a detector at the slits to see which slit the electron actually goes through, the interference pattern disappears. You get two piles. The act of measuring which slit the electron goes through forces it to go through one slit. And when it only goes through one slit, there's nothing to interfere with, no pattern, just two piles. The universe changes its behavior based on whether you're watching, not metaphorically. literally. Observation affects reality at the quantum level. Feynman called this the central mystery of quantum mechanics. And he was right. This is where common sense completely breaks down. Common sense says things have definite properties, whether you look at them or not. A tree falling in a forest makes a sound even if no one hears it. But in quantum mechanics, that's not necessarily true. The electron doesn't go through a specific slit until you check. Before you check, it goes through both. Measurement creates reality, or at least measurement forces reality to pick a specific state out of many possible states. Your brain hates this. Your brain wants things to be definite, to have properties, to exist in specific states whether you're looking or not. But the universe doesn't care what your brain wants. Let's talk about another example. Quantum tunneling. Imagine you have a ball. You throw it at a wall. Common sense says if you don't throw it hard enough, it bounces back. The ball needs enough energy to break through the wall or go over it. Otherwise, it stops. But in the quantum world, particles don't always obey this rule. Sometimes a particle with less energy than needed to overcome a barrier just appears on the other side. It tunnels through, not by going over, not by breaking through, by quantum tunneling, existing on one side, then existing on the other side, without ever being in the middle. This sounds impossible. It is impossible according to classical physics, but it happens constantly. Radioactive decay works because of quantum tunneling. Particles inside an atomic nucleus don't have enough energy to escape, but sometimes they tunnel out anyway. The nucleus decays. We've measured this. We've built technologies based on it. Scanning tunneling microscopes use this effect to image individual atoms. Your common sense says particles can't pass through barriers. They don't have the energy to overcome. Common sense is wrong. Now, let me talk about entanglement, because this is where things get really weird. Take two particles. Entangle them. This means putting them into a quantum state where their properties are correlated. Now separate them. Put one particle on Earth and one particle on Mars. Light years apart if you want. Here's what happens. If you measure the spin of the particle on Earth and find it spinning up, the particle on Mars instantly has a definite spin-off down. Instantly. Faster than light could travel between them. Einstein hated this. He called it spooky action at a distance. He thought it proved quantum mechanics was incomplete, that there must be some hidden variable we're missing, some underlying reality that makes this make sense. But he was wrong. We've tested this. We've done the experiments. Quantum entanglement is real. Measuring one particle really does instantly affect the state of the other particle, no matter how far apart they are. Now, before you get excited, this doesn't let you send information faster than light. You can't use entanglement for communication. The results of measurements on both ends appear random. It's only when you compare the results afterward that you see the correlation. But still, two particles separated by any distance remain connected in a way that defies common sense. There's no signal traveling between them, no hidden communication, just a fundamental connection built into the quantum state. Feynman understood something crucial about all of this. He understood that the universe is under no obligation to make sense to creatures who evolved to hunt gazelles on the African savanna. Our brains are pattern-matching machines built for survival, not for understanding reality. And the reality we encounter in physics is nothing like the reality our ancestors needed to navigate. Here's what Feynman would say. Stop trying to visualize it. Stop trying to build a mental picture that matches your everyday experience. You can't. It's impossible. The quantum world doesn't work like the everyday world. It has different rules. Accept that. Learn the math. Make predictions. Test them. But don't expect it to make intuitive sense, because it won't. Let me give you another example of common sense failing. Time. You think time flows at the same rate everywhere. You think a second is a second no matter where you are or how fast you're going. Wrong. Time is relative. A clock on a GPS satellite runs faster than a clock on Earth, not because the clock is broken, because time itself runs at different rates depending on how fast you're moving and how deep you are in a gravitational field. This is not a small effect. GPS satellites have to account for relativistic time dilation or they'd give you the wrong position. The math is built into the system. Without correcting for relativity, GPS would be off by miles within hours. Think about what this means. Time is not universal. There is no cosmic clock ticking away the same for everyone. Your time and my time only match if we're at rest relative to each other and at the same gravitational potential. If you get in a spaceship and fly away at high speed, your clock runs slower than mine. Not from your perspective. From yours, everything seems normal. But when you come back, less time has passed for you than for me. You've aged less. You've experienced less time. This is real. We've tested it with atomic clocks on airplanes. We've measured it with particles in accelerators. Fast-moving things experience less time. Feynman loved pointing out how absurd this seems. He'd ask, if you're in a spaceship moving at 99% the speed of light and you look at your watch, does it run slow? And the answer is no. From your perspective, the watch runs normally. It's the outside universe that seems weird. Time dilation is symmetric. You think the outside world's clocks are running slow. They think your clock is running slow. Who's right? Both of you? There is no absolute time. Time is relative to your reference frame. Here's another one. E equals mc squared. You've seen this equation. You probably think you understand it. Energy equals mass times the speed of light squared. Fine. But do you really get what it means? It means mass and energy are the same thing. Not similar, not related, the same. Mass is frozen energy. Energy is liberated mass. They're interchangeable. You can turn mass into energy. You can turn energy into mass. They're two forms of the same underlying thing. When you burn gasoline in your car, you're converting a tiny amount of mass into energy. The exhaust weighs slightly less than the fuel and oxygen you started with. The missing mass became heat and light and motion. When particle accelerators smash protons together, they create new particles out of pure energy. Energy from motion becomes mass in the form of particles that didn't exist before. The universe can do this because mass and energy are equivalent. Your common sense says matter is matter and energy is energy. They're different categories. Wrong. They're the same category viewed from different angles. Here's what this means for the universe. The total amount of mass energy is conserved. You can shuffle it around. You can change its form, but you can't create it or destroy it. Every bit of mass in your body was energy at some point. After the Big Bang, the universe was nothing but energy, pure radiation. As it cooled, some of that energy condensed into particles, into matter, into atoms, eventually into you. You are frozen starlight, condensed energy that's been cycling through various forms for 13.8 billion years. Feynman would tell you this, and watch your face to see if you got it, really got it. Not just nodded along, but felt the weight of what it means. Now let me talk about something that really messes with people. The uncertainty principle again, but deeper this time. Heisenberg told us you can't know position and momentum simultaneously. But there's more. The energy of a system and the time you measure it are also uncertain. The more precisely you know the energy, the less precisely you know when the system has that energy. This leads to something bizarre. Virtual particles. In empty space, in a perfect vacuum, particles pop into existence out of nothing. Particle-antiparticle pairs appear, exist for a tiny fraction of a second, then annihilate each other and disappear. This happens constantly, everywhere, right now. Empty space is not empty. It's seething with virtual particles flickering in and out of existence. How is this possible? Because of the uncertainty principle. If you look at a tiny enough time scale, energy conservation doesn't have to hold. The universe can borrow energy to create particles as long as it pays the energy back quickly enough. The smaller the time interval, the more energy you can borrow. This is not speculation. We've measured it. The Casimir effect demonstrates this. Put two metal plates very close together in a vacuum. Virtual particles that are too large to fit between the plates can't appear there, but they can still appear outside the plates. This creates a pressure difference. The plates are pushed together by the imbalance of virtual particles. We've measured this force. It matches the predictions. Empty space has structure, has energy, has particles constantly appearing and disappearing. Your common sense says empty means nothing. Physics says empty is full of something. Let's talk about another common sense failure. Cause and effect. You think cause comes before effect. You think if A causes B, then A must happen first. In everyday life, this is true. You push a domino, it falls. Cause then effect. But in quantum mechanics, this gets fuzzy. When you have entangled particles and you measure one, the other instantly takes on a correlated state. There's no time for a signal to travel between them. So which measurement caused which result? Neither. Both. The measurements are correlated, but there's no causal arrow from one to the other. They're connected outside of time, beyond causality in the normal sense. Or consider quantum tunneling again. A particle doesn't have enough energy to overcome a barrier. It can't escape. But then it does. What caused it to tunnel through at that specific moment? Nothing. It's random. Truly random. Not random in the sense of we don't know what caused it. Random in the sense that nothing caused it. There is no deeper mechanism, no hidden variable. The universe is fundamentally probabilistic. Some things happen without cause. Feynman embraced this. He didn't try to restore causality or determinism to quantum mechanics. He accepted that the universe is genuinely random at its core, that probabilities are fundamental, not just expressions of ignorance. Here's what he'd say. The universe doesn't owe you determinism. It doesn't owe you causality. It doesn't owe you comprehensibility. It is what it is. Your job is to figure out what that is, not to insist it should be something else. Let me tell you about another area where common sense fails. Temperature. You think temperature is how hot something feels. You think cold is the absence of heat. Sort of right, but missing the deeper truth. Temperature is average kinetic energy of particles. Hot means particles moving fast. Cold means particles moving slow. Absolute zero is where particles stop moving entirely. Almost. Because of quantum mechanics, particles can never completely stop. Even at absolute zero, there's still 0-point energy. Still quantum jitter. Still uncertainty, preventing everything from being perfectly still. But here's the weird part. Temperature can be negative. Not in the sense of being below zero. In a deeper sense. In certain systems, you can arrange things so that higher energy states are more populated than lower energy states. This is called a population inversion. And when you calculate the temperature of such a system using statistical mechanics, you get a negative number, negative absolute temperature. And here's the kicker. Negative absolute temperature is hotter than any positive temperature. It's hotter than infinite temperature. The scale wraps around. We've created systems with negative absolute temperature in labs. They exist. They're real. Your common sense says negative temperature should be colder than zero temperature. Physics says negative temperature is infinitely hot. Common sense loses again. Now, let me talk about something Feynman loved. The path integral formulation of quantum mechanics. This is his contribution to quantum theory. And it's beautifully weird. In classical physics, A particle moves along one path, a definite trajectory. You can calculate it using Newton's laws. In quantum mechanics, Feynman said, the particle takes every possible path simultaneously, every single path from point A to point B. The straight path, the curved path, the path that loops around 3 times, the path that goes to the moon and back, all of them. Every possible path contributes to the final probability of the particle arriving at point B. Each path has a phase associated with it, and all these phases interfere with each other. Most paths cancel out, but some paths reinforce each other, and the ones that reinforce most strongly are the ones near the classical path. This is why large objects seem to follow definite trajectories, not because they actually follow one path, but because all the other paths cancel out through interference. But for tiny particles, the other paths don't completely cancel. They contribute. They matter. This is why quantum particles can tunnel through barriers and exist in superposition. They're exploring all possible paths. Common sense says a particle moves along one path. Feynman says it moves along every path. And somehow, the math works. The predictions match experiments. This formulation is how we calculate quantum probabilities in particle physics. Let's talk about something else. Antimatter. For every particle, there's an antiparticle. Same mass, opposite charge. An electron has a positron. A proton has an antiproton. When matter meets antimatter, they annihilate. They convert completely into energy. Total conversion. E equals mc squared at maximum efficiency. This is real. We make antimatter in particle accelerators. We use positrons in PET scans. Medical technology relies on antimatter annihilation. But here's the weird part. Feynman and others realized that an antiparticle is mathematically equivalent to a particle moving backward in time. A positron moving forward in time looks exactly like an electron moving backward in time. This isn't just a mathematical trick. It's a deep insight into the structure of space-time. Particles and antiparticles are time-reversed versions of each other. What does this mean? It means at the fundamental level, time symmetry is built into particle physics. The laws work the same forward and backward in time, with particles and antiparticles swapped. Your common sense says time only goes forward. Physics says time direction is more flexible than that. Here's another example. Conservation of parity. For a long time, physicists assumed the universe treats left and right symmetrically. Mirror image processes should work the same way. Then in 1956, experiments showed this is false. Weak nuclear interactions violate parity. They treat left and right differently. The universe has a handedness. If you showed an alien a video of certain particle decays, they could determine which direction is left and which is right in your reference frame. This shocked everyone. Common sense says left and right are arbitrary labels. Physics says the universe has a preferred orientation. Feynman loved this. He loved every time the universe surprised us. Every time nature revealed another layer of strangeness. He didn't see it as a problem to solve. He saw it as a feature. The universe is weird. Good. That makes it interesting. Let me talk about renormalization. This is a technical topic, but it reveals something profound about how physics works. When you try to calculate the properties of an electron using quantum field theory, you get infinities. The math blows up. The electron's interaction with its own field creates infinite energy, infinite mass, infinite charge. This seems like a disaster, a sign that the theory is broken. But physicists figured out a trick called renormalization. You absorb the infinities into the definitions of mass and charge. You treat the infinite bare quantities as unobservable. What you measure is the renormalized mass and charge, which are finite. This sounds like cheating, like sweeping problems under the rug. But it works. The predictions match experiments to incredible precision. Quantum electrodynamics, the theory of how light and matter interact, gives predictions that match experiments to 10 decimal places. It's the most precisely tested theory in all of science. Feynman helped develop this theory, and he won the Nobel Prize for it. But even he thought renormalization was philosophically ugly. He called it a dippy process, a shell game, something that works but doesn't feel right. And yet, it's correct. The universe allows this kind of mathematical manipulation. It produces finite, testable, accurate results from seemingly infinite nonsense. Your common sense says a good theory should be clean and simple all the way through. Physics says a good theory makes accurate predictions, even if the math is weird. Here's something else Feynman emphasized. The role of probability in quantum mechanics is fundamental, not just practical. In classical physics, if you flip a coin, it's deterministic. The result is determined by the initial conditions. The coin's spin, the air currents, the surface it lands on. If you knew all these perfectly, you could predict the result. We use probabilities because we don't know the initial conditions precisely. But in principle, it's deterministic. In quantum mechanics, this is not true. When an electron decays, when a photon gets absorbed, when a particle tunnels, the outcome is genuinely random. There are no hidden variables determining the result. We've tested this with Bell's theorem and Bell inequality violations. Local hidden variable theories are ruled out by experiments. The randomness is real, built into the fabric of reality. God plays dice. Einstein hated this. He wanted determinism. He wanted a clockwork universe where everything is predetermined. But experiments sided with Feynman and Bohr. The universe is fundamentally probabilistic. Feynman would tell you this is okay. Probability doesn't make the universe less real or less beautiful. It's just how things are. Accept it and move on. Let me talk about symmetry. Physicists love symmetry because it constrains what laws are possible. If the laws of physics are the same everywhere in space, that's translational symmetry, and it leads to conservation of momentum. If the laws are the same at all times, that's time symmetry, and it leads to conservation of energy. If the laws are the same no matter which direction you face, that's rotational symmetry, and it leads to conservation of angular momentum. These connections between symmetry and conservation laws are deep. They're not obvious. Emmy Noether proved this theorem in 1915. Every continuous symmetry corresponds to a conservation law. This is one of the most beautiful results in physics. And it means the structure of physical law is tied to the geometry of space-time. Your common sense doesn't know about this. Your common sense doesn't connect symmetry to conservation. But the universe does. Here's another place common sense fails. Scale. You think the laws of physics should be the same at all scales? They're not. At human scales, friction matters. Air resistance matters. Things slow down and stop. At astronomical scales, friction is negligible. Planets orbit for billions of years without slowing down. At atomic scales, quantum mechanics takes over. Particles exist in superposition. Uncertainty dominates. At subatomic scales, virtual particles appear and disappear. The vacuum fluctuates. At the Planck scale, space and time themselves might break down into quantum foam. The laws change, or rather, different laws dominate at different scales. Classical mechanics works for everyday objects. Relativity works for fast objects and strong gravity. Quantum mechanics works for tiny objects. We don't have one unified theory that works perfectly at all scales. Not yet. Maybe never. The universe operates on different principles at different levels. Common sense says the same rules should apply everywhere. Physics says each scale has its own regime. Now let's talk about measurement in quantum mechanics. What counts as a measurement? This is called the measurement problem. and nobody has a fully satisfying answer. In the equations of quantum mechanics, systems evolve smoothly and deterministically. Wave functions spread out, superpositions develop. Everything is continuous and predictable. But when you measure, the wave function collapses. The system jumps from being in multiple states to being in one specific state. This collapse is discontinuous, non-deterministic, completely different from normal evolution. What causes collapse? Where's the boundary between quantum superposition and classical definiteness? Is it when the particle interacts with a measuring device? When the device interacts with a human observer? When the observer becomes conscious of the result? Nobody knows. There are different interpretations of quantum mechanics that give different answers. The Copenhagen interpretation says, measurement causes collapse, but doesn't define measurement precisely. The many worlds interpretation says, there's no collapse. The universe branches into multiple versions. Every possible outcome happens in some branch. You just experience one branch. The de Broglie-Bohm interpretation says, particles do have definite positions. The wave function guides them, but they're always somewhere specific. Feynman didn't commit to any interpretation. He'd say, learn to calculate, make predictions, test them. The interpretation is philosophy, not physics. This frustrated people. They wanted answers about what's really happening. Feynman would say the math is what's really happening. Your need for a story behind the math is your problem, not physics' problem. Here's the deep point. The universe doesn't care about your need for comprehensibility. It doesn't care about your mental models. It doesn't care about your intuition. The universe is what it is. And if that happens to be strange and counterintuitive and impossible to visualize, so be it. Your job as someone trying to understand reality is not to insist reality conform to your expectations. Your job is to conform your understanding to reality. This is hard. This requires humility. This requires accepting that you might never truly understand in the intuitive sense. But you can still make progress. You can still learn the patterns. You can still make predictions and test them. That's what science is. Not perfect understanding, but progressive refinement of models that work. Feynman was a master at this. He didn't pretend to have cosmic insight. He didn't claim to understand the deep meaning of things. He just worked out the math, made predictions, and checked them against experiments. And when the predictions worked, he moved on. When they failed, he tried something new. No dogma. No attachment to ideas that don't work. Just ruthless empiricism. Let me tell you about one more thing. The arrow of time. Time seems to flow in one direction. Past to future. Eggs break but don't unbreak. Milk mixes with coffee, but doesn't spontaneously unmix. Entropy increases. Disorder grows. This is the second law of thermodynamics. But here's the puzzle. The fundamental laws of physics are time-symmetric. They work the same forward and backward. If you showed a physicist a movie of particles colliding, they couldn't tell if you're playing it forward or backward. Both directions obey the laws. So why does time have an arrow at the macroscopic level? Why does entropy increase? The answer is statistics. If you have a system with many particles, there are far more disordered arrangements than ordered arrangements. When particles move around randomly, they're much more likely to end up in a disordered state simply because there are more ways to be disordered. The universe started in a very low entropy state after the Big Bang, very ordered, very special. Since then, entropy has been increasing, not because of a law that forces it to increase, but because statistically it's overwhelmingly likely. The arrow of time emerges from statistics, not from fundamental law. Feynman understood this. He knew the second law is different from other laws. It's probabilistic, not absolute. In principle, entropy could decrease. It's just stupendously unlikely. Your common sense says Time flows forward, because that's how time works. Physics says time is symmetric at the fundamental level. The arrow of time is an emergent property of statistical systems. Here's what all of this adds up to. Common sense is a product of evolution. It's a set of heuristics that worked well enough for survival in a specific environment. But the universe is not limited to that environment. The universe includes things moving at relativistic speeds, things existing in quantum superposition, things with negative temperature, things where cause and effect blur, things where time dilates and space curves. Your common sense was never meant to handle any of this, and that's okay. You can learn new intuitions. You can build new mental models. They won't feel natural at first. They might never feel natural, but you can get better at working with them. Feynman would tell you to stop fighting it. Stop trying to force quantum mechanics into a classical picture. Stop trying to make relativity feel like Newtonian mechanics. Accept that these theories describe reality accurately, even though they don't make intuitive sense. Use the math. Trust the experiments. Let go of the need for everything to feel right. Because here's the thing. Reality is under no obligation to make sense to you. The universe was here billions of years before humans evolved. It'll be here billions of years after we're gone. It doesn't care whether you understand it. It doesn't care whether it fits your mental categories. It just is. And the remarkable thing is that despite all this, we can still make progress. We can still figure things out. We can't visualize quantum wave functions, but we can calculate with them. We can't imagine curved spacetime, but we can use the equations. We can't picture what an electron really is, but we can predict how it behaves. That's the power of mathematics. It lets us work with concepts that are beyond our ability to visualize. It extends our thinking beyond the limits of our intuition. This is what Feynman mastered. He was brilliant at calculations, at seeing patterns in equations, at finding clever ways to solve problems, but he never claimed to understand it all deeply. He'd say if someone asks you what an electron really is, the honest answer is, we don't know. We know how it behaves. We know the mathematical description. But what it really is, that's maybe not even a meaningful question. The map is not the territory. The equations are not the reality. They're descriptions, models, tools for making predictions. And they work. They work incredibly well, better than any other tools humans have ever devised for understanding nature. But they're still just maps. The territory remains mysterious. Here's the beautiful part. Feynman loved the mystery. He didn't see it as a failure of understanding. He saw it as an opportunity. Every weird result, every counterintuitive prediction, every place where common sense failed was a chance to learn something new about how the universe actually works. He approached physics with wonder, with playfulness, with the attitude that if something seems impossible, maybe your assumptions about what's possible are wrong. Not cynicism, not frustration, delight. The universe is weirder than we thought. Good. Let's figure out how weird it actually is. This is the attitude we need. Not demanding that reality conform to our expectations, but letting reality teach us what's possible. Being willing to abandon common sense when the evidence demands it. Following the math wherever it leads. Accepting strange conclusions if they make accurate predictions. This is hard. It goes against every instinct we have. We want reality to make sense. We want it to fit into familiar categories. We want to be able to picture it, but we can't always have what we want. And that's okay. The universe doesn't owe us comfort. It doesn't owe us comprehensibility. What it does give us is consistency, patterns, laws that we can discover and use, even if we don't fully understand them in an intuitive way. Feynman showed us how to work with this, how to be comfortable with mystery, how to make progress even when the territory is strange and counterintuitive. Learn the math, do the calculations, make predictions, test them. When they work, use them. When they fail, try something else. Don't get attached to ideas. Don't defend theories just because they feel right. Follow the evidence. Trust the experiments. Let nature be the judge. This is the path to real understanding. Not the kind of understanding where everything feels familiar and makes intuitive sense, but the kind of understanding where you can make accurate predictions about how reality behaves, where you can build technologies based on weird quantum effects, where you can send spacecraft to other planets using relativity, where you can split atoms and harness nuclear energy. Practical understanding, mathematical understanding, understanding that works even if it doesn't feel satisfying to your intuition. That's what Feynman gave us. Not comfort, not easy answers, but a way forward. A method for making progress even when the subject matter is strange beyond comprehension. So when you feel frustrated that quantum mechanics doesn't make sense, remember that's the point. It's not supposed to make sense in the everyday way. It's supposed to make predictions. And it does, better than anything else. When you feel confused about relativity and time dilation and length contraction, remember your confusion is evidence that you're taking it seriously. If it seemed easy and obvious, you wouldn't be getting it. The confusion is part of the process. Work through it. Do the problems. See how the math works out. Check the predictions against your own calculations. And gradually, you'll develop a different kind of intuition. Not the kind where you can picture what's happening, but the kind where you know what equations to use and what results to expect. That's physicists' intuition. And it's built not by making things simple, but by working with the complexity until it becomes familiar. Feynman could calculate quantum probabilities in his head. He could see patterns in Feynman diagrams instantly. He had deep intuition about particle physics. But it wasn't common sense intuition. It was learned intuition, built from thousands of hours working with the math. You can build that too. Not by trying to make quantum mechanics feel like everyday life, but by working with quantum mechanics until it becomes your everyday life, until the equations feel natural, until you stop asking what it means and start asking what it predicts. That's the shift Feynman made. That's the shift every physicist has to make. From demanding comprehensibility to accepting functionality, from asking what it is to asking what it does, from trying to visualize to being content with calculation. And here's the paradox. Once you make that shift, once you stop fighting the weirdness, something remarkable happens. You start to see beauty in the strangeness. You start to appreciate how elegant the mathematics is, how deeply connected different phenomena are, how much structure there is even in the apparent chaos. The universe is weird, but it's weird in consistent, mathematical, beautiful ways. The weirdness has patterns. The confusion has structure. And when you learn to see those patterns, when you learn to work with that structure, you're seeing reality more clearly than common sense ever could. Common sense is a lie. A useful lie for navigating everyday life, but a lie nonetheless about how the universe fundamentally works. Physics is the truth. Strange, counterintuitive, impossible to fully visualize, but true. Verified by countless experiments, confirmed to absurd precision. The actual description of reality. Feynman knew this. He lived it. He taught it. He showed us that you don't need to make physics make sense. You just need to make it work. And when it works, when the predictions match reality, when the theory lets you build new technologies and understand new phenomena, that's success. That's understanding. Not the comfortable, familiar understanding of common sense, but the real, accurate, powerful understanding of mathematical physics. The universe doesn't care about common sense. Feynman knew that better than almost anyone, and he showed us how to make progress anyway. How to work with reality as it is, not as we wish it would be. That's the lesson. That's what we need to remember. When physics seems impossible, when the math seems crazy, when nothing makes sense anymore, you're probably on the right track. Keep going. Trust the mathematics. Follow the evidence. Let go of your need for it to feel right. Because the universe is under no obligation to make sense, and that's what makes it worth studying.